Good day to everyone. This is Matt from Geo Communications. I'll go ahead and get started here. We'll start with a couple introductions, and as people are joining, I'd like to welcome everyone. If you haven't been familiar with our webinar series here, we try to do one every month, and this is our March edition, of course, of the webinar. And it's actually a fun time for us here at GL. I mean, we get to express ourselves a little bit. We involve our engineers and our developers in the process, and whoever's working on the project or the product that we're talking about, we get them involved in the webinar from behind the scenes and putting the presentation together to actually talking and doing the webinar. So it's generally a fun time for everyone. They get to express themselves, and it's good for our morale internally to do this. We think it's helpful to everyone outside of GL as well. Our representatives have given us some good feedback over the years here on it's a good way for them to keep up with our products, keep up with what's going on here at GL Communications, upcoming news and so forth. We try to announce a little bit on the webinar. So with that being said, today we're excited to talk about VoIP ATM test solutions. So if you're on the webinar, you probably know what ATM stands for, but it's Air Traffic Management. So this is a timely webinar because we're coming off about 2 to 3 weeks removed from a show that we did called the World ATM Congress Show, where GL had a booth displaying these exact products that we're going to be talking about. So we probably met a few of you there, and if so, thanks for stopping by, and we're glad you joined us again here. I guess I should introduce myself. My name is Matt Yost. I'm joined on the webinar today by our senior developer in this arena named Srinivas. Srinivas is going to help out with part of the webinar, and I'll hand over to him here after the introductions, and then I'll grab it back to do a portion of it at the end. Also on our team here, on our webinar team is Sanjeev Kulkarni. Sanjeev is going to be monitoring your questions throughout. So I'd encourage you to, if you have some questions or if there's a topic that we're talking about, even on the screen, you know, on the slide that we're on, if you have a question, just alert Sanjeev through the GoToWebinar toolbar there on your screen. And we have a small group today, so we may just interrupt the webinar right then and there and try to address your question. So alert him of the questions, and he will interrupt us, and we'll try to address questions as we go. What we're planning to do is have a short break about halfway through where we can address questions or any outstanding issues. We'll open it up to anybody who wants to have a comment. And then we'll, of course, at the end, like we always do, we will open it up to the floor to everybody, the participants, and we will answer and take as much time as needed to address all questions and comments. So with that being said, I'd like to go ahead and get started here. One final note is we're going to be recording this, and we always do with our webinars, and we always post them on our website. So all of our previous webinars are posted on the website. This one will be posted in a couple days, so you can review it at your leisure or have a colleague review it and so forth. So with that being said, let's go ahead and get started. Jump right in. I'll give you a quick introduction to Geo Communications if you're not familiar with it, with us. Geo Communications has been around since 1986, so we're an established company here. Our headquarters are in the Gaithersburg, Maryland office here in the United States, but we have offices, a couple offices around the world, and we have representatives throughout the world. We got started in engineering consulting services. We have a lot of engineers that support local, state, and federal government. But we also, in the early 90s, got dabbled into test and measurement equipment. So we started in the test equipment, telecommunications test equipment business, where our niche was basically PC-based test equipment. So easy to use, easy to operate, research and development labs, very detailed test equipment that we provided. Way back when we got started with a T1 card, and it's only grown ever since then, and we've got products in all types of communications arenas at the moment. So for today's webinar, I'll just go over the agenda with you really quick. We're going to talk in the air traffic management world. There's a protocol, ED137 protocol, which is a variant of SIP. Its roots, its foundation is SIP, which is a voice over IP protocol. And it's called ED137. We here at GL have ED137 emulators. So we have what we call a MAPS ED137 radio emulator, a telephone emulator, and a recorder emulator. So we're going to give you a little background on what those are. The MAPS acronym stands for Message Automation Protocol Simulation or Simulator. And it's our sort of overarching architecture on how we initiate, produce, test, simulate protocols. MAPS, if you're familiar with old TDM protocols like ISDN, PRI, SS7, and so forth, MAPS has a MAPS ISDN version, a MAPS SS7 version, a MAPS GR303 version. So we've got all types of MAPS versions that address each protocol in communications. The one we're talking about today will be ED137. So we'll talk about our emulators. We'll also get into our monitoring solutions. So similar to a non-intrusive monitoring solution that we have is something called packet scan. So if you're familiar with how a Wireshark is used and so forth, packet scan is similar in nature, but it brings to the table a lot more on the voice analysis and voice detailed analysis arena, where we get into, if you're familiar with ED138 monitoring solutions, we are presenting those in packet scan. NetSurveyor Web and NetSurveyor Web Lite is a complement to packet scan, where you can store in a database all of this information and mine it at your will, show different statistics on your network, look for trends, look for anomalies, events of interest, and so forth. So we'll show you a little bit about that. And then finally, I'll jump back in and I will talk about the critical delay and voice quality measurements that we offer in the air traffic management world. So that's our agenda. With that said, I'll just repeat, if you have questions throughout, we're a fairly small group today, so I would encourage you to just raise your hand, alert us through the GoToWebinar panel, and we will try to stop and address the comment and then move on. So with that said, let's go to the next slide, and I'm going to hand it over at this point to Srinivas, who is our expert in all things air traffic management, ED137, ED138. Srinivas.
Yeah, thanks, Matt. Hello, everybody. This is Srinivas here. Today, I'm going to present simulation and monitoring solutions for ATM network. So as you can see in this diagram, it shows a typical VoIP ATM network with basic components. And we are trying to show the roles that our test solutions can play in testing this network. Okay, we can emulate the controller working position or a VCS or ground radio station, and also the recorder servers. So basically, as Matt told, we have 3 emulators to simulate the radio, telephone, and recorder interfaces as per ED137 specifications. And on the monitoring side, we have products called Packet Scan and Netzer Web. So Packet Scan can capture all the IP traffic in the ATC network non-intrusively, through the mirror port in the network, and it can measure voice quality metrics like MOS, packet loss, jitter, delay in the network on each and every captured call. Okay, and optionally, packets can also act as a probe and send call records to central database. Further, our web application, that is Net Surveyor Web, it can be used to monitor and generate key reports for network quality. And it also helps in remote monitoring of the ATM network. Let's begin with the emulators first. So all these emulators use a generic framework, as Matt already described about MAPS architecture. So basically it stands for message automation and protocol simulation. So, and this is the architecture that we are using uh, to simulate all the protocols in the telecom domain, basically in the networks like TDM, VoIP, 2G, 3G, and LTE networks. MAP stands, as the name indicates, MAPS framework provides ability to customize messages and protocol state machines, or you can call it as a call scenarios easily. So because of its flexibility, you can create any kind of custom scenarios. That is the most advantageous part of this framework. And basically, it's a script-based application with easy to learn plain English scripts. So first one is the MAPS ED137 telephone emulator. So it's a lightweight software-only product supported on Windows 7 and above operating systems. It has a very easy to configure and use graphical interfaces, and it also supports the Python client. Yeah, this image shows a use case where MAPS ED137 is simulating a ground-to-ground call against a real controller working position or a VCS to perform the functionality verifications. It can simulate ED137 Volume 2 telephone interface, and recently we have enhanced it to support the C version also. Uh, it can simulate hundreds of CWPs in a system with a single license, and it can also generate bulk calls to perform load testing or to create the background traffic. And it also supports the audio codecs used in this ATM arena, like G71 A-Law, U-Law, and G729. On the call, like send and record audio files, send and detect digits and tones, and we can also send real voice using microphone and playback the voice on the call to the speaker connected to the system. So this is a profile configuration window for creating multiple controllers. You can see here we have created 10 controllers. Each controller can have its own set of call parameters or ED137 parameters. So you can see the ED137 parameters, like what should be the call subject, priority, WG67 version, WG67 call type. So similarly, we have a list of all these parameters. And the base parameters include like the defining the SIP URL contact address for the user. Okay, and it supports all the call services. Uh, Supports all the call services like call hold, transfer, call pickup, multi-destination calls, preset, and broadcast conference calls. Okay, and we can also apply impairments to RTP traffic like packet loss, latency, duplicate, and out of sequence packets in the generated RTP traffic. So by this way, we can create the uh, degraded nature of the IP traffic, so that we can evaluate how the other end or the device under test is going to handle it or behave for these impairments. And it can also simulate call failure scenarios with the SIP 4XX, 5XX, and 6XX errors. to verify how the real CWP or the VCS is going to handle it. This is the call generation window. So you can see here, this is the script sipcall control.gls. Okay, it's a GL's proprietary script. Okay, but a very easy to learn script. Okay, so this is the script which is going to simulate all the ground to ground call scenarios. And in the next column, we can select the controller using which we want to place the call. And under the call info, once the call is established, it will display the other end party, the other control for end controller. And this is the script execution button. Okay, or it is also, we can call it as a button to establish the call and terminate the call. And next, the status column, it will keep updating the call status as and when it progresses. And these are the event buttons. So here we'll have a list of events. So these events can be like, I want to keep the call on hold, or I want to transfer to a third party kind of thing. Okay, so we can select those options and apply those options on this call. And results, actually, so we within the script, user can define his own, like the pass and fail criteria for the test. So as and when those criteria are encountered, so it will post the appropriate result based upon the call scenario. And next, actually, we have a total iterations here. For example, we can define a call to run for multiple iterations. Okay, and it when it is running, like it will also show the progress, like how many iterations have been completed and all. Okay, and apart from that, we have another option called wherein we can have multiple calls selected here, and all those calls can be placed at once simultaneously, or they can be made to run sequentially or in a random nature. Okay, and we can also specify the duration when the next call has to uh, start executing. And so these kind of tools will help in creating the random nature or the sequential execution of certain test cases against the device under test. Okay, and for each of the call, we also display the call graph, wherein it will display all the messages exchanged between the two parties, along with the useful informations like what is the call type, how much time it took to establish the call, or something like that. And when you click on these messages, you'll be able to, on the right side, you'll be able to see the message decodes. And apart from this, we also have a scheduler which can run a test at a particular predefined time. Like I can schedule a test to run daily or a weekly once, something like that. And this slide shows how we can simulate multiple controllers, each with a unique IP addresses, and they are also simulating different call types in the telephone. So that concludes about telephone emulator. Now we'll move on to the radio emulator. Radio also has a similar specifications as telephone. So in this slide shows MAPS ED137 radio simulating both controller and a ground radio station or a radio. Okay, basically it emulates ED137 volume 1 radio interface as per B and C versions. The same software supports both versions, and user can make a choice when he invokes the products, whether he wants to run it in the B version or C version. And it also gives a choice for user to make whether he wants to simulate the controller working position or the ground radio station. It can simulate hundreds of controllers and radios in a single system with one license. Okay, it can be used to test radio interfaces within real CWP, VCS, radio, and radio gateways. Okay, and it also supports all radio call types, PTT types, and additional SIP and SDP parameters as defined by ED137 specifications. So all the parameters mentioned in the specifications have been included, and they can be configured per controller or radio. So this slide shows the radio profile configuration. Okay, we can simulate hundreds of radios again. Okay, each configured radio has its own set of parameters and settings, like what should be the radio type. See, you can see here transmitter or a receiver or a transceiver, and it can have a permitted user list. It can have the frequency configurations. Okay, and it supports all the 4 RTP header extensions. Basically, these extensions are like climax time delay, signal quality index, dynamic delay measurement, and radio remote controller. So this is the call reception window at GRS node. Okay, it automatically groups the calls established to particular radio, and we are also using some color codes to identify the calls to a particular radio. So you can see here, this is the script that is handling this A to ground call, and this is the radio, and this is the controller which has made a call to this radio. So you can see here there are 3 radios in this image, and so all these calls have been established. It gives all the other details like what is the PTT ID and other informations, and it will also be updating the statuses. And below there are event buttons to apply the impairments or play the voice to the speaker, or we can apply the squelch by clicking on the start squelch. And as shown in telephone, again here also we are giving the detailed call graph. Okay, so apart from the signaling messages, it will also indicate all the radio signaling informations like PTT on off, squelch on off, and the other things like PTT mute has turned on, PTT summation. So all these informations will also be provided along with the 4 RTP header extension decodes. And again, there is a message decode. Okay, and yeah, the radio supports all radio features like WG67 key in event, link session management, call preemption, PTT priority handling, etc. And we have also provided scripts to perform the PTT and the squelch operations periodically or randomly on the AZ call. And it can also detect and count synchronous transmissions due to synchronous transmissions occur due to either pilot transmissions or the controller pilot transmissions. So this slide shows how we can simulate hundreds of controllers or radios to simulate different radio call types. The next slide shows like the different ED137C features supported in this emulator. So basically here the important ones are the radio receiver multicast operation. Okay, and the other one is cell call tone transmission. So apart from that, there are some minor features, and they have also introduced the test PTT type here. And it also, in case of W67 key in event package, now the radio is going to indicate the frequency ID of the radio. And yeah, there have been provided option to not to terminate the calls whenever there is a frequency change. So controller can opt for that option also. So and the radio version is also updated to radio.02. So these are some important features introduced in the C version. So next one is a MAPS ED137 recorder emulator. Okay, it has similar specifications as radio and telephone emulators. So this image shows the recorder interface being emulated by MAPS ED137 recorder at different nodes like CWP, GRS, and uh, the recorder itself. Okay. Again, we can simulate a recorder interface from multiple CWPs and radios in a single instance of MAPS. And it can also simulate both air to ground and ground to ground recording sessions in the same product. And most importantly, it supports all three audio transport methods mentioned in the ED137 specifications. So basically, these are like embedded binary data wherein payload will be carried over the RTSP messages, and independent TCP, and third one is independent UDP. So this slide shows some of the common use cases of a recorder emulator. In the first case, the recorder vendors can use emulators to simulate air to ground calls recording towards the recorder. Okay, so in this case, we can either act as a CWP and create the RTSP sessions towards the recorder interface, and we can perform all the air to ground scenarios, or we can also act as a GRS and perform the air to ground scenarios, recording scenarios towards the recorder. Similarly, we can also create the ground to ground call recording sessions towards the real recorder, so that we can verify the recorder's functionality. And at the same time, since it supports multiple controller working positions, and also the bulk, we can generate a bulk RTSP sessions towards the recorder. We can also perform the load testing on this recorders. So the case 3 is about for the CWP or VCS vendors who want to, uh, who want to test the recorder interface by emulating a recorder. Similarly, case 4 is about uh, for the radio vendors who want to test the recorder interface by emulating a recorder. So this slide shows profile parameters for recorder interface at CWP. So again, we can create multiple controllers here, and we can also configure different ED137 parameters so that we can simulate both air to ground and ground to ground recording call scenarios towards the recorder. We can have the custom call record data properties and operations. Okay, so adding those properties and operations is very easy here. And that can be done through the profile configurations. And recorder server can record and playback the voice on the sessions, and it can also store the call record data to CSV files. Okay, and we have a scripts that allow to perform PTT or squelch operations on the session periodically or randomly based upon the configurations. So the next slide shows the way to make RTSP sessions to recorder. So you can see here RTSP session is established between from the controller working position 001 towards the recorder at 1.59 IP address. Okay, and you can see the PTT button. Whenever we want to simulate the PTT, we can just key and unkey the PTT button here. Okay. Uh, yeah, again, sessions can be run repeatedly for a defined number of iterations. Okay, and multiple scripts can be configured to run simultaneously, sequentially, or randomly. So these are, and there is also a scheduler that can help to run multiple scripts at different intervals as defined by the user. So these are the features of this maps framework, uh, which allows to provide automation of the test cases. And we can also create hundreds of RTSP sessions towards the recorder to perform load testing. So for example, in reality, recorders need to be recording hundreds of calls 24/7. So it becomes necessary that recorders go through all the load and performance test before they have been implemented in the field. Okay, so for that, Maps Recorder helps in creating those all those random and bulk scenarios towards the recorder. So that's all about the emulators. I think we can have a short break for questions. Let me know if you have any questions on the emulator section.
Yeah, we have a question here.
Okay.
Yeah, how do you detect the controller or pilot simultaneous transmissions?
Yeah, for example, the controller pilot, in case of pilot transmission, it is actually only the squelch bit will be set for on, and the SCT bit will indicate that this is a simultaneous transmission. Okay, but the PTT bit will be off. Okay, so it makes sure that there is no any PTT transmission detected. Okay, it is purely the squelch that is coming from multiple aircrafts. Okay, in case of controller pilot induced SCTs or the synchronous transmissions, so when we are receiving the R2S or the RTP packets from the radio, actually, that RTP packet will have PTT bit set and also the squelch bit set. So that indicates that the other end radio has detected some transmissions that are happening that are initiated by some of the controllers. So that is how we'll detect these uh, controller pilot induced synchronous transmissions.
Yeah, we have one more question. How many controllers or radios can be simulated with one license?
Yeah, we can simulate up to 200 controllers or radios with a single license.
Hello, good morning. I'm Marius Irlbeck from Eurocontrol in Maastricht. My question is about how you manage to detect the simultaneous calls when involves an ATCO and the pilot. Yes, I understand the squelch and the PTT are both active at the same time, but this happens also when it's only the controller transmitting. And I would like to know how you differentiate between an, let's say, squelch coming from the controller and the squelch coming from an aircraft call.
Okay, so basically what happens is there are a few scenarios. For example, the controller has started the transmission first and then the squelch is detected. Okay, or it might happen simultaneously. So based upon such scenarios, we'll be able to identify these things. But again, like it is a it is very difficult based upon the sequence how they are happening. We can decide about the controller and controller to pilot and pilot to pilot induced transmissions. Okay.
So you are taking into account also the delays, let's say, over the network, or the transmission activation time, or the receiver activation time, or even the VCS internal delays, or I just need to understand how you decide whether a simultaneous PTT and squelch are due to the ATCO transmission or are due to an simultaneous transmission between ATCO and pilot.
Yeah, we are not looking at the delays actually. So it is about the I mean, frankly, it is very difficult to identify that this one, because since we are we are just a simulators. Whatever we are receiving is the PTT header indications. So we just try to based upon the bits set in the RTP header extension, we are trying to judge like this is like a controller pilot or the pilot induced simultaneous transmissions.
And it's also a very, I don't know, a way to indicate this this event, because it's not mentioned. I mean, it's not present in any of the RTP streams. It's just the result of your calculation. So how do you present this to the user?
Yeah, with respect to user, like we'll be displaying it in the call graph only. So whenever it is detected, we'll also display the counts. For example, we show the parameter like a PPSCT counts and CPSCT. PPSCT is pilot induced SCTs, and CPSCT is a parameter called controller pilot induced SCT. So whenever these things will be happening, we'll show it in the call graph. Say for example, I can show you here. Say for example, like some events will be indicated on the call graph, indicating like how many CPSCT and PPSCT counts have happened until now.
Okay, so in the end, it looks similar to the SCT, which is presented by the receiver itself.
So we'll be notifying that SCT event also, which has been detected. And apart from that, we'll also give the counters like until that SCT, how many PPSCT and CPSCT have been occurred on this call until now.
Okay, clear. Thank you.
Thank you. So any other questions?
No, Srinivas, we can continue.
Okay. So yeah, we'll move on to the monitoring solutions for this ED137. So we have two monitoring solutions, Packet Scan and Netzer Web Lite, that can work hand in hand to provide a real-time and a historical analysis of ATM network. This image shows a simple ATC network. Okay, Packet Scan can capture all the IP traffic in this network non-intrusively through the mirror port of the switch. Okay, it can process all these captured frames, segregates them into call, and then it will measure the voice quality on each of these calls. Okay, these these metrics involve like both the signaling statistics and also the RTP statistics or the voice quality statistics. And it can also send call detail records. So for each call, it is going to build a call detail record. Okay, and it is going to send it to the database server. So our web-based application, that is Netzer Web, can query the database and show real-time and historical call detail records, and also the it can present the graphical reports. Say for example, how the MOS has varied over a period of time. So we'll begin with the Packet Scan first. So Packet Scan is a lightweight software-only product, and it again runs on the Windows platform. It is used to monitor overall network health and to solve deep protocol issues. For example, if there are any call failures and all, you may want to dig into the messages to see what has gone wrong. Okay, and it can capture in real time for a infinite duration, and it can also process the offline traces. So moving to the next slide, it can capture and monitor air to ground and ground to ground calls in the network. Okay, and it provides a summary and message decodes of the captured calls. So it can decode SIP, RTP, and all RTP header extensions as per ED137 specifications. So this helps in analyzing the exchange of the radio parameters like the PTT bits or the squelch bits or the SCT bits and all. So it helps in analyzing what has been exchanged between the controller and the radio, okay, on the per call basis. And it also provides the capture and view filters for the analysis of traffic of interest. For example, I can put the capture filters to capture only the SIP and RTP traffic, so that I'm not bothered by other traffic, which will be usually more. And it can also import and export Wireshark trace files also. So if you have a Wireshark trace file captured at some of your locations, and if you want to perform a deep analysis of that capture, so you can just import into packet scan, and it will be able to do the complete analysis. So this slide shows the call summary view, where we are displaying all the calls captured in the network along with the complete details. So you can see here these red lines give the signaling information like who is the caller and callee, call established time and duration. And the other two black lines, rows, will give the incoming and outgoing traffic details. For example, in case of A to ground, the first one is the PTT session, and second one is the squelch session. Okay, and it gives the complete details like what is the conversational MOS score measured on both the directions, packet discarded, missing packets, duplicate packets out of sequence, average gap, delay, jitter. Okay, so all these parameters are measured and provided on each of the uh, calls. So this is what the call detail record is going to contain. It is going to contain all this information that you are seeing on the screen. And you can also see that for a good quality scores without any degradations, the MOS score is around 4.20, which is excellent. And there are few calls which have been highlighted here with a very low MOS scores like 2.21 or 1.47, and these are because of the packet losses encountered on the call. So around 25% packet loss is there, packet loss observed on these calls actually. And apart from this, it also provides the counters for PTT squelch, PTT summation, PTT mute, and SCT counters that have happened in the network. So these counters are provided per call and also for the aggregated capture. Okay, and we can also record and play the audio on the calls. We can detect digits and tones, and it also provides a graphical analysis of the calls such as call graphs. And we also have a graphs to show the MOS, jitter, and latency variation during the call for a particular call for the throughout call duration. Okay, and we have one more feature that is called triggers and actions features, uh, which allows user to define thresholds or filters for the calls and perform certain actions on the filtered calls. For example, I can define filter to filter calls with low MOS score, and I may want it to be notified through a email notification with details like recorded audio or the trace of that call. Okay, so it will help. Yeah, this triggers and action features will help in that way. So uh, it's also helps in like a non-intrusive monitoring of your network. So whenever there is a degradation or something, you will immediately get the notifications. So next one is the second monitoring tool, that is a Netzer Web Lite. So we have two types here. One is Netzer Web, which can handle. It is like a full-fledged. It can handle a more call detail records or a more traffics. It has a huge database based upon the requirement. Okay, it is a separate. It is provided as a separate appliance. But Netzer Web Lite is something like it can be installed in the probe system, that is a packet scan system only. So it is limited by the storage space up to 9 GB. Okay, So this will be helpful when you are monitoring only a low traffic. Okay. Yeah, the advantage it is yeah, compared to features, both in both the products, the features wise it is all same. It is only the capacity of the database which is going to make the difference. Okay. And yeah, so this web-based network surveillance, it's a web-based network surveillance system for air traffic monitoring. So we can uh, access this web application through any mode, like we can access it through our laptops, mobiles, or any tabs kind of thing. So it helps in remote monitoring of the ATM network. And it can the main network Netzer Web full version, like the higher version, it can work with multiple probes. So you can have a one centralized database which will be fed by multiple probes installed in the network. Okay. And it has a scalable and flexible architecture to define custom filters and reports. For example, we, like as I told, we can have our we are providing some default reports, but user can define his own filters and reports and display them graphically. So it also helps in real time and historical analysis, wherein, for example, in the database you have stored a data for a 1 month. Okay, so you can check the patterns of, for example, failure calls for the last 1 month. Okay, or a last 1 week. Okay, so that way it helps in analyzing the historical patterns of your network. And yeah, this is the call detail record view. You can see here, this is the signaling information, and again there is a two-way traffic. Okay, so similarly for each captured call, we are going to display all these details. And apart from this, there are some quick CDRs links where if you want to look at only the air to ground calls, so you can just click on this one. It will filter out the only the air to ground calls or ground to ground calls. Or if you want to have a look at poor MOS score calls or failed calls. Okay, so there are some quick links which are based upon the filters defined. Okay, so user can have his own quick CDRs, and he can also define his own filters also. Okay. So next one shows a detailed view of a selected call. Okay, so here we'll be listing out all the events that have happened on the call. Say for example, the PTT on and off events, squelch on and off events. Okay, and for each PTT and squelch, we are calculating the MOS score freshly, and all these scores will also be displayed for each of those transaction cycles or the transactions. So in the next slide, we are showing the default ED137 reports that we are providing. So you can see here in the first graph, we are plotting the MOS scores measured for all the calls and how they are varying day by day. Okay, so you can see here the category has been like a desirable CMOS, something like 4 to 5, and acceptable CMOS, it could be like from 3 to 4. Okay, reachable connection is something like a 2 to 3, and not recommended CMOS is something like less than 2. Okay, so we are using different color indications to differentiate those things. Okay, and also if you want to see these 124 calls which have encountered a non-recommended CMOS, so you can just uh, click on this item, and it will display only those calls which have encountered this MOS score less than 2. So by this way, it makes it very easy to analyze the calls, identify the calls, and analyze the degradations in the network. So similarly, we have a average packet loss encountered. So you can see here packet loss from 1 to 2%, or packet loss with less than one packet. That means with a 0 packet loss, there are 4,248 sessions. Okay. Similarly, we have a PTT and SCT counters for pilot induced SCT or the controller pilot induced SCT, and these are the failure causes. The calls failed because of different signaling failures. For example, dialing unknown number, or there is no answer, server errors, server is busy, kind of thing. So we can define, a user can define his own categories, and he can display, uh, he can modify the graphs and display it accordingly. And he can also choose the duration from when to when he wants to display. So it can be like last 24 hours or a 1 day or a last 1 week, or he can specify the dates also from when to when he want to do the analysis. So accordingly, the graphs will be displayed for the selected duration. So so again, in the Netzer Web also, we provide this triggers and actions features, wherein we can define the triggers based on some thresholds. Say, for example, as I mentioned, we want to filter out only the calls with less than MOS scores with less than 3 or something like that. And we can perform different actions like email notification with reports, log events, or visual and audible alarms can be provided. And we can also configure to generate daily, weekly, and monthly reports through email. So it will automatically generate these reports and send it to the configured email addresses. Okay. So so this covers the monitoring solutions for ATM network. Okay. So I'll just now hand over to my colleague Matt to present the next slides.
Okay, thanks, Srinivas. So for the last portion of our webinar, we're going to be talking about the critical delay and voice quality measurements that can be made in this ATM world. So one thing I'll say before we jump in is, and I mentioned it earlier at the beginning, GL, it basically has tested measurement equipment, test products for all of telecom, and we have taken a couple of our products that have been well established in the industry, the telecom industry, for testing voice quality, for testing IP packet networks, some hardware that we have developed over the years, internally developed over the years, and we've applied them to this air traffic management world for doing some of these delay tests and voice quality tests. So with that said, I'll present to you how we're doing that. And the first slide that we'll show you here is just a very simple network, an ATM network, where we got a couple of the components that are, very block diagram oriented components of the network. So controller 1, it goes through a legacy VCS, maybe to a VoIP gateway, and then it obviously gets converted to IP at that point, goes through the VoIP backbone of the network over to maybe a VoIP VCS, so a new ED137 enabled VCS, over to controller 2. Also, along the way there, you obviously can be talking to GRSs. So we have on that leg up to a radio, and then ultimately up to a plane. So this just shows you some of the components there. Now the next slide, when we enable it, you're going to see where GL has positioned our products with varying products, and I'll explain to you a little bit more about that. But as we show here, the points in the network that we can test, I will explain to you sort of the different points and sort of the analog points, the IP points, and so forth. So let's go ahead and enable that for us. Yes. So here you see same diagram, same elements of the network. We're able to place a a product, a piece of hardware, a small piece of hardware at different points in this network. Now, as you can tell, these different points are either analog points, as you're going into a legacy gateway there's a T0 is an analog interface. So we have the ability through what we call our audio analyzer, which you'll see a little bit more about here in a slide or two. It has the ability to connect to maybe your legacy VCS or your ED137 VoIP-enabled VCS through the audio interface. So we can take the place of the controller, the microphone and the speaker of the controller, and we can inject audio into that device, and we can receive audio from that device and record it. So we have access at T0 and at T4 directly into a VCS or a CWP through this audio analyzer, we call it. Now, at T2, T5, and T3 there, as you're going across, those are obviously IP interfaces within the network. So we have something else, another hardware product we call Packet Analyzer. And the Packet Analyzer is a long-standing product here at GL, which small piece of hardware that can allow packets, IP packets to flow through it. And filters can be set so that it can be looking for packets of interest as things are flowing through it. And when it sees these packets of interest, it can basically forward those packets to a timing device, and you'll know exactly when those packets of interest happen. So as we show that here, we've got the audio analyzer at the analog inputs, and we have the packet analyzer sitting at the IP elements of the network. And these things work in harmony in the sense that they both, the audio analyzer and the packet analyzer, can send their events of interest, their timing events, down to what we call internally an event data logger. The event data logger in GL's system is where the timing, the ultimate timing, gets put on to these events. So to be a little bit more specific, different call scenarios happen throughout this network. You've got things like PTT turning on, PTT confirm messages coming back. We can time the deltas between those things happening from analog side to the IP side, or maybe from IP to IP in a sense. So PTT confirm, just a couple scenarios, squelch break, of course, main and standby switching and so forth, remote muting. So all of these scenarios, these call scenarios, we have the ability to be looking for them. The packet analyzer is sitting there looking for, it has a specific filter set up to look for that packet of interest, that event to occur, and it has the ability to forward that over to the event data logger, and ultimately the timing is centralized at that point, and we can do deltas between all of these T0 through T5s. Okay, we also have the ability to time actual voice from any point in this network. So we can be detecting voice, not just, for instance, IP packet, header, flipping from 0 to 1 in a PTT header, changing from 0 to 1 or so. We can actually be detecting the voice at that point. So when the voice comes on or the voice goes away, we can see that, we can detect that, and we can test the delay of voice itself from different points in the network. So these tests, I'm not getting into the nitty-gritty of how we actually do it, but I'm telling you that these tests are all possible. Now, who are these tests applicable to? That's very key here. Well, we have found great interest from ANSPs who want to verify. They have to get some confidence that the vendors that they are bringing in are meeting timing regulations, timing thresholds that they have set for different events to happen. So they're very interested in having this piece of test equipment, this test system, to be verifying these timing measurements throughout their network. So ANSPs are a key customer of ours when it comes to doing this. Vendors, equipment vendors, VCS vendors need to know how long it takes for their VCS to process these different events. VoIP gateway vendors need to know how long it takes for their VoIP gateway engines to process these events. So these are radio vendors need to know that as well. So different equipment vendors, as well as ultimately the vendor's customer, the ANSPs, need to know these things. Quickly, I've talked about it a little bit. The audio analyzer piece of hardware that we have, it emulates a controller, so it has the ability to PTT and send and record audio. When it does these different things, PTT on, PTT off, send audio, record audio, detect audio, all of these things, all of these events, the start of these events can be sent out. This is all hardware-based timing. So Windows is not involved in any of this. So it's very precise. And these events, the start of these events can be sent out to an oscilloscope, as we're showing here at the bottom, or that event data logger that we talked about earlier. It has the ability to send and record voice, as I mentioned. So it has the ability to do voice quality measurements from end to end, from different points in the network. And we're using the latest standards, the telecom standards that are out there, which are PESC and Polka, to do that. We also have some IP standards, R factor, E model, and so forth that we show. All of these products have the ability to be set up for automation, and we have CLIs and APIs available so that third-party tools can use them. The next slide shows the packet analyzer. Again, similar in nature in the way it looks and so forth, but this is a product that has IP packets flowing through it. So what we call the span ports there in the middle is the network, from network A to network B, we'll call it. And a filter is happening between those two ports, and anytime a packet of interest that you have set up meets that filter, that packet and so forth is dropped out the drop port and sent over to the event data logger. That also can trigger a TTL event to come out, and on the right side of the picture there can be sent over to an oscilloscope. So I've actually, in our lab, and some of our customers are doing this, different events from an analog point in your network to an IP point. I have taken a TTL output from an audio analyzer, run it into channel 1 on the oscilloscope. I've taken a TTL output on the packet analyzer, run it into channel 2 on the same oscilloscope, and I'm able to see visually on the oscilloscope the delta between those timing events, those events of interest. So those things can happen. We have packet filtering that's based on layer 2, layer 3, and layer 4, and so forth. And one other thing I'll mention there, it's all API, CLI accessible for automation on that packet analyzer. This is showing you a little automation, or animation, I should say, of the how these packets flow through the packet analyzer. So they are flowing from port 2 over to port 3, and from port 3 back over to port 2. Whenever they meet the criteria, the filter that we have set, they are sent to this drop port, port 1 in this case, and then forwarded over to our event data logger. Okay. And the filtering mechanism that we use, we can talk about in great detail, but we have a good depth of filter where we can catch all events that you may be interested in. So we've set up these filters to be able to fully customize them and you have full access to, bit per bit there. So Voice quality comes into play, of course. What I've talked about before with the audio analyzer and the packet analyzer has been timing measurements, delay measurements. Voice quality is very important from end to end. At any point in the network, as I mentioned earlier briefly, we have the ability to inject an audio file, which we call a reference file in the voice quality world, and then wherever the other side of that network, it traverses the network, whatever elements of the network it traverses, there is a recorded audio file that's grabbed from the other side. And those two files, the reference file and the recorded audio file, are presented to our voice quality tester, our algorithm, and it spits out a ITU standard voice quality score, which again is set up through the ITU standards, and that quality score is known through the industry. So if you tell a person in the telecom world outside of ATM that you've got voice quality in your network of 4.1, they'll know what that means because it's standardized. So that's important to understand. Voice quality can be done with these products. Okay, so that would be it. We appreciate your time here. We presented it. We went a little over on the timing, so we apologize for that. But we'd like to open it up for anybody to ask any questions about any parts of this, and we can go into a little bit more detail. We can answer anything for you. So please, Sanjeev is monitoring there. You can get a hold of him, and he can present questions to us. But we do appreciate your time on this. We're excited about these products. We've had them for many years now. They've gained a lot of traction in the ATM industry. Anything, Sanjeev?
Yeah, I'll just unmute Marius. He has some questions.
Sure.
Yeah, it's about the packet scan. You always mentioned the analysis based on call. Yeah, so every call is analyzed. What exactly is the definition of the call?
Yeah, hi Mario. So it is actually the call, for example, in case of air to ground calls, okay, we'll be considering the call as when the SIP call is established, okay. But as far as the measurement is concerned, okay, measurement of the voice quality. So what we are doing is once that air to ground call is established, the every PTT and the squelch that is happening, we are calculating a separate MOS scores and packet loss, all these quality metrics for that particular PTT or the squelch cycle, and we'll be posting these things.
Okay, so every, let's say, active PTT and active squelch separately will define a call. It's not necessarily from, let's say, invite till the buy events.
No, the way we call it as the invite to buy is treated as the signaling call, and there will be a kind of, we call it as the sessions. So sessions mean here the PTT and squelch are the sessions within that call.
So actually between invite and buy, you may have multiple calls, yeah?
Yeah.
Okay, for us it's important because we don't terminate the call in terms of invite and buy. We only have an invite, and then the call stays up permanently for the air-ground communication.
Yes, for air to ground, that's the case, of course. And so what we've done, as Srinivas said, is for every PTT, we'll call it session, is what we're internally calling it, and for every squelch session, we sort of treat that as an individual call in a sense. So we show that individually, and we show parameters for that particular session, even though the signaling has been established long ago, of course. But
okay, and this exercise can take place also when, let's say, the packet scan doesn't have any invite in the sequence, because the invite was probably
before
long before we started the monitoring.
Yes, that's correct.
Yeah,
Okay.
that is correct. So you can see here, this is the squelch on and a squelch off. This is one transaction, or you may call it as a one call. So for this squelch transaction, we are displaying the conversational Morse code, the missing packets, and all these details. Similarly, for the PTT here, and PTT has turned off. So for every what we call as a session, or you may call it as a call, so we are making independent measures, and we are displaying them. If
Okay.
there is a signaling call, it is fine. Otherwise, we'll also be able to analyze the independent PTT and squelch also.
Okay, this is great. And beside the MOS calculation, is there any audio level indication for each call?
No, we do not have the audio level indication. I mean, yeah, we do. I mean, we have a detailed view actually, wherein we are giving this oscilloscope display. Okay, so where we can show the audio levels. Okay, uh, but we may have to provide a average audio level, include that audio level within the call summary.
Would this be possible, let's say, for the next release, or is feasible to be done in the software? Like you calculate the most, just to calculate also a kind of average value of the audio in every call.
Yeah,
Yeah.
I think we can calculate the audio level.
So one thing Srinivas mentioned there, I'll reiterate, is, as these sessions or calls are happening, if a PTT session is up, you're actually able to look at the spectrum analyzer or the oscilloscope in real time and watch it, and you can get a real-time look at what the levels look like. But but if you come back in a post-process mode and you want to see a session that happened an hour ago, we can provide that average audio level for that session, but at the moment we are not putting that in there. But it can be done.
Okay, I think this would be, at least in our case, will be useful because sometimes when we get problem reports, sometimes is that the problem occurred because the audio level was not sufficient for whatever reason.
Okay.
And this probably would be very helpful to trace back what happened.
Okay. Yeah.
And I have a last question on the Net Surveyor. You mentioned that you are able to indicate the percentage of the packet loss. In this ED137, the RTPs are, let's say, of kind of two flavors: the audio packets and the R2S packets.
Right. Yes.
Do you treat them separately when you make these statistics, or they are, let's say, taken all together, like just counting them as one packet regardless the nature of?
No, we are treating them separate because whenever there is a voice, I mean only the RTP, so we are calculating the voice quality statistics on that particular PTT or squelch when the audio is active. So we are not mixing the R2S keep alive packets here.
Right.
So that means how do you calculate the percentage of the loss then? You just average them, or if you count them separately?
Yeah, for example, we will calculate the total audio packets, okay, that have been received versus the missed packets. Okay, based upon the sequence number, we'll find out how many packets should have been received. That is the total RTP packet it should have been received. Out of that, I have lost, say, for example, some 100 packets. Okay, so we'll take the percentage of that.
So we do not we separate the audio and the R2S, and they are not combined in their packet loss. Yeah, in their records. R2S sort of stands alone, and we obey all of the R2S rules of if we miss one and for a certain amount of time we'll kill the session and things like that. But we do not. All of our packet loss statistics and so forth are based on the audio RTP packets only.
Okay. So R2S is not taken into account for the statistics.
Not in that. Yeah, that's correct. Not in that statistics. I mean, Srinivas, do we show any R2S sort of like, for instance, if we miss an R2S packet, one out of the zillion that come through, do we show that anywhere?
No, I think yeah, we can provide that parameter.
Okay. Yeah, because we're keeping track of them along the way, obviously, because we are obeying all of those R2S rules. So we are keeping track of those. We can show those.
I mean, there is a total count of the RTP packets received, but right now there is no direct parameter which is saying that so many only R2S packets are received and so many are dropped, kind of things.
Okay.
Mm-hmm. And is this measurement window how long it is? When you calculate the percentage, you should use probably a window. I hope it's not the whole day.
Well, no, it can be set up to be what you want. Okay, this particular graph here is showing you a day by day, but it's very easily changed in the software where we can show it, every 10-minute slice or every 5-minute slice or every hour and so forth. So that's just a parameter to change on how you want to see it.
Oh, okay.
Yeah.
Great. Thank you.
Okay, thank you for your questions.
Yeah,
Sanjeev,
I think that's about it.
That's the questions. Okay.
Yeah.
Okay. One other note for the remaining people: if you do have any other questions, the easiest place to ask them would be send an email to info@gl.com. So it's info@gl.com. Very easy to remember, and just possibly just say you were on the webinar and you have an additional question, or you wanted to get some more details about a particular thing you saw here. So Srinivas or myself or somebody will reach back to you and start helping you out with that. So with that said, thank you, everybody. Thank you for your time today. We appreciate it. It was good talking to you all, and we will conclude it now. We'll look forward to possibly attending our next webinar, which will be toward the end of April. Okay, with that said, thank you. Bye-bye.
Thank you, everybody. Bye.